All right, so we're going to talk about the unit circle today. And the unit circle is one of those things that can be really confusing because a lot of times you're just given a picture of the unit circle and told, oh, this is important, you need to know this. So what we're going to look at is actually where the unit circle comes from, what it all means, and how you can generate it yourself using what we already know of geometry. So here on the screen we have a picture of the unit circle, and it looks kind of terrifying if you've never seen it before, or even if you have seen it before. Sometimes it can be a little bit overwhelming because you're looking at it and you're going, why does it say pi over 4? Why are there so many square roots and degree symbols? What's happening? So to start, we're going to actually look at where the unit circle comes from, and to do that we're actually going to start with the x and y axis. So I'm going to take away the unit circle that's already there, and we're just going to look at the x and y axis. So on the screen right now we have the x-axis and the y-axis going from -2 to +2 in each direction, but we know from what we understand of the Cartesian plane, really this is going to go on forever. We're just only looking at this specific section. And what we're going to do is we are going to construct a circle in the middle of the coordinate plane. So it's centered at the origin here at 0, 0. So we're centered at 0, 0, but even here, centered at 0, 0, we're really going to look at the entire circle. So our circle is centered at 0, 0. It has a radius of 1 because it goes from the origin out to 1 in any direction. So we have a circle with a radius of 1 centered at the origin. And our goal is to figure out some points that are on this circle. So maybe we want to know, what is this point, or this point, or this point? And all of those points are literally just points in the xy axis, or in the xy plane. It doesn't matter that they're sitting on a circle. I can take away the circle and I still have points in the middle of the graph that I want to know the coordinates of. So for example, this point right here, if I was just estimating, I might say that it has an x coordinate of, I don't know, 0.9 maybe. It's really close to 1. And then a y coordinate of, I don't know, about 0.25. Those are just estimations. So our goal is to be able to figure out exact coordinates for some points on the circle. But we're not just going to pick any random points on the circle. We're going to pick points that tend to show up a lot in mathematics. So there's some angles that end up being important in mathematics, specifically a 30-degree angle, a 60-degree angle, a 45-degree angle, a 90-degree angle. Those are all kind of important angles in mathematics. So we're going to look at those angles. So let me pull up my protractor, and we're going to look at 30 degrees first. So I'm zooming in even more. We're still on the coordinate plane, but now we're really just looking at this circle, which is the unit circle, since it's 1 unit in radius. And we're going to look at the angle of 30 degrees. So we're looking at an angle that goes from the x-axis, from the positive x-axis, to 30 degrees. That's where we measure when we talk about a 30-degree angle. So we have a 30-degree angle here. And we're going to look at the coordinate of the point that is on the circumference of the circle. So if we extend that 30-degree angle out, we could keep extending it if we wanted to, but we're just going to stop when we get to the circumference of the circle. We want to know what is the x-coordinate and the y-coordinate for that point sitting on the edge of the circle. So the point that is right here, regardless of whether or not we have the circle there, that point still exists on the graph. So we want to know what is the x-coordinate for that point and what is the y-coordinate for that point. Well, my x-coordinate is something less than 1, and my y-coordinate is also something less than 1, but maybe closer to 1/2 here. So we want to know what is the horizontal distance and what is the vertical distance to get our x and y coordinate. So to figure that out, my x distance would be the distance along the x-axis until I get beneath my point. And then my y distance would be the distance on the y-axis, but I'm actually going to shift that over to be able to construct this triangle right here. And the reason that I want to construct this triangle is because I know that once I construct this triangle, I'm going to have a 90-degree angle. And then my angle that I started with was 30 degrees. And if I solve for the missing angle, I have 60 degrees. So I have a 30, 60, 90 triangle. And in geometry, we learn about 30, 60, 90 triangles. And we learn that there are special rules for the sides of 30, 60, 90 degree triangles. So we're going to look at just that triangle. And so I'm going to get rid of that and redraw it a little bit neater. So here we go. There's our 30, 60, 90 degree triangle. And I'm going to get rid of everything else for just a second so that we're only looking at our triangle. All right, so we have a 90-degree angle here, 30 degrees, 60 degrees. And we had the radius, or the hypotenuse in this case, which is 1. And the reason I know the hypotenuse is 1 is because this was actually the radius of the circle, and we know the radius of this circle is 1. That's the way it was constructed. So our triangle that we're looking at has a hypotenuse of 1. That's going to be important to help us solve for the missing sides. So now the rules for a 30, 60, 90 triangle. In a 30, 60, 90 triangle, we know that the short leg is equal to 1/2 of the hypotenuse, or a lot of times it's said that 2 times the short leg is equal to the hypotenuse. So the short leg is 1/2 of the hypotenuse. So in this case, I'm going to label my short leg y because this vertical distance will be my y coordinate. And so y is equal to 1/2 times the hypotenuse, which is 1. So 1/2 times 1 gives us 1/2. So my y value over here, my height, is 1/2. Then in a 30, 60, 90 triangle, the long leg is equal to square root of 3 times the short leg. So I'm going to label the long leg of my triangle x because that's the side that's going to give me the x coordinate for the point I was looking at on the unit circle. So if x is my long side, I can now say that x is equal to square root of 3 times the short leg, which we found out earlier was 1/2. So square root of 3 times 1/2 gives me square root 3 over 2. So I'm going to get rid of all of this work down here because that was just my formulas. And now I'm going to put all of this back onto that unit circle. So now I have this triangle constructed, and this horizontal distance is square root of 3 over 2, and I've labeled that as x. So this point right here on the circle has an x coordinate of square root of 3 over 2. And then my vertical distance, my y value, I have labeled as 1/2. So then my y value for that point is 1/2. So that point on the circle right here has an x coordinate of square root of 3 over 2 and a y coordinate of 1/2. And even if I take away that circle, this coordinate in the middle of the graph has an x coordinate of square root of 3 over 2 and a y coordinate of 1/2. Oops. So that is the first most important piece of information for the unit circle. We have now found one point on the unit circle. So we're going to keep going. Now that we found this point, we're going to find a different point. So for the next point, we're going to look at the next specific angle that we like, which is 45 degrees. So 45 is another one of those special angles that we want to look at. And again, just like earlier, I can construct a triangle with an x distance and a y distance to figure out the x and y coordinate for that point on the circle. So let me again pull up my slightly better drawn triangle. Here we go. So we have a 45, 45, 90 triangle now that we're going to be looking at. Sorry, let me rewrite that. 45, 45, 90. And again, we're going to get rid of everything else so that we can just look at the triangle. So 45, 45, 90. Our hypotenuse is 1 again because that hypotenuse was the radius of the circle. So our hypotenuse is 1. Now in a 45, 45, 90 triangle, the rule is that the hypotenuse is equal to the square root of 2 times the leg. So square root of 2 times the leg. So then, some creative math here. If our hypotenuse is 1, then our leg, which we could call x or y, since this is a 45, 45, 90 triangle, it's isosceles, which means the sides are going to be the same. So square root of 2 times, let's just say x for now. Well, then if I want to solve for x, I would have to divide both sides by square root of 2. So square root of 2 divided by square root of 2 would be 1. So we'd end up with 1x. And on the other side, I have 1 over the square root of 2. But in math, we don't like to leave radicals in the denominator. We don't like to have square roots on the bottom of the fraction. So instead, we do a process called rationalizing the denominator, which means we multiply by whatever's in the denominator. So square root of 2 over square root of 2, which still is equal to 1. Anything divided by itself is 1. So we're not changing the value, we're just rearranging it. So square root of 2 times 1 would give us square root of 2 in our numerator. Square root of 2 times square root of 2 would be square root of 4, which we know is just 2. So our x value is square root of 2 over 2. But also, we said earlier, this is a 45, 45, 90 triangle, so it's isosceles. So if our x value is square root of 2 over 2, then our y value is also going to be square root 2 over 2. And I'm going to get rid of a lot of this extra information. So our x value is square root 2 over 2, and our y value is square root 2 over 2, okay, for this triangle. So that means if I then plot a point on the circumference of this circle, I'm going to have an x-coordinate at square root 2 over 2 and a y-coordinate at square root 2 over 2. And then I'm going to get rid of that triangle. Well, I'm actually going to erase part of it first and then get rid of that triangle. There we go. All right, so now I have 2 of the points that I want on the unit circle. I'm going to keep going though. So now I'm going to look at 60 degrees. So we've done 30. Oops. We've done 30. We've done 45. And now we're going to move on to 60 degrees. So here's 60 degrees. And just like we did earlier, we can construct our triangle to figure out those points on the circle. So now I want to figure out what is this point on the circumference of the circle. And now I have a 60-degree angle. Again, this is the angle from the positive x-axis up to that hypotenuse, or up to that radius. So that's 60 degrees. We have 90 degrees down here, which gives us 30 degrees at the top. So now I have a 30, 60, 90-degree triangle with a radius of 1. Hopefully that sounds familiar. We've already done a 30, 60, 90-degree triangle with a radius of 1. I'm going to take this triangle that we were working with earlier, and I'm going to rearrange it a little bit. So let me flip it, rotate it a lot, and hopefully you can see that these triangles are the exact same. Well, they would be if I was better at drawing them, but these triangles are the exact same triangle, which means, let me try and put this back, that the coordinates for this triangle, this first triangle that we had, are going to be the same as the coordinates for the second triangle, but they're not in the same position. So for this first triangle, we said that this shorter side was 1/2. Well, that means for our new triangle that we're looking at, the short side is still 1/2. But this time, the 1/2 for the short side is not the y value, that's going to be our x value. And then for this first triangle, we said that the longer side was square root 3 over 2. So for our new triangle that we have constructed, this longer side is also going to be square root 3 over 2, but now that's going to be our y coordinate. So the point I'm trying to make here is that we are going to have the same exact numbers for our coordinates, but they're going to be switched. So instead of square root of 3 over 2 first, we're going to have 1/2 first, and then square root of 3 over 2 will be second. So same numbers, but swapped for 30 degrees and 60 degrees. So now we have all of these points in the first quadrant. And again, even without the circle there, those points are still just random points on a graph. Okay? We're just specifically looking at them. So bringing back my circle for a second. And I can keep going with some other points. So for example, this point hopefully is pretty easy to label on the graph. It's 1 over 0 up. It's just 1, 0. Again, that one's pretty easy, especially if we take away the circle. We have just 1, 0. That's a point you've always been able to read on a graph. This point up here has an x-coordinate of 0, a y-coordinate of 1. And I could keep going over into this quadrant. I have an x-coordinate of -1 and a y-coordinate of 0. And down here, I have an x-coordinate of 0 and a y-coordinate of -1. All right, so I have these points that I started with. My goal now is to get those same points around the rest of the circle. So I am going to take my triangle that I was already dealing with, and I'm going to start moving it around the entire circle kind of creatively, because I know the lengths of this triangle sides, so I can use those to figure out coordinates in other quadrants. So now I'm going to take this triangle, and I'm going to move it over here to this side. And I'm going to plot some new points over here on this side. So for this point over here on this side of the triangle, or sorry, on this side of the unit circle, I have the same triangle that I had over here for my first point. So this short leg over here is still 1/2. This long leg is still square root 3 over 2. So my x-coordinate for this point is square root 3 over 2 coming from the long side, and my y-coordinate is still 1/2. However, because this is not just a circle, this is a point on a graph, when I'm in quadrant 2, I have -x, positive y. So that means for this point that I'm plotting, I need to have negative square root 3 over 2 because my x needs to be negative. All right, and then I'm going to take my same exact triangle, and I'm going to creatively rotate it again, and I'm going to drag it down into this quadrant. And I need to go back and erase some things. There we go. Get rid of that. So now I can come down here, plot a point on the circumference of the circle, and write the coordinates for it. Now I am in quadrant 3, and in quadrant 3, x is negative and y is negative. So both my values are going to be negative, but I'm still repeating the same numbers. So now it's negative square root 3 over 2, negative 1/2. And then I'm going to go back to my triangle, and I'm going to rotate it again. Shift it over into the 4th quadrant, plot my point on the circumference of my circle. Now in quadrant 4, we have positive x and negative y. So I'm still writing the same numbers. So positive x would be positive square root 3 over 2, but negative y, so negative 1/2. All right, and now I am done with that first triangle. So notice all of these points that I've plotted have corresponding x and y coordinates. The only difference is the signs. Now I can do the same thing with a new triangle. Now I can go to my 45, 45, 90 triangle and follow the same exact process with it. So I'm going to reflect it, translate it over, and plot my points. Now for this one, the x and the y value were the same. They're both square root 2 over 2. And I know that now that I'm in quadrant 2, I need a negative x and a positive y. So negative square root 2 over 2, positive square root 2 over 2. Now I'm going to come back to my triangle. Not like that. Come back to my triangle and rotate it. Reflect it, translate it, and plot some more points. So now I can plot this point in the 3rd quadrant. In the 3rd quadrant, x and y are negative, so negative square root 2 over 2, negative square root 2 over 2. Then I can go to my triangle again, reflect it one more time, translate it over, plot my point. Now that I'm in quadrant 4, I'm going to have positive for my x, negative for my y. So positive square root 2 over 2, negative square root 2 over 2. And I can get rid of that triangle. And now I have one triangle left that I need to look at, which is this one, which came from 60 degrees, right? 60 degrees was my original angle that I was looking at. So now I'm going to take that triangle and reflect it, move it over, plot my point, and I'm just doing the same process over and over and over again. So now for this point, my x coordinate that corresponds to it is 1/2. My y coordinate is square root of 3 over 2. So my x coordinate is 1/2, but now that I'm in quadrant 2, I need negative 1/2. Y is still positive, square root 3 over 2. Then I take the triangle, move it around. Again, if I was better at drawing, this would match up a little bit better. Plot my point. And then this time, my coordinates are still 1/2 square root 3 over 2, but now they're both negative, so negative 1/2, negative square root 3 over 2. And one last time, moving my triangle to end up in the 4th quadrant. Again, plot my point. Now I have positive 1/2 for my x, negative square root 3 over 2 for my y. Because remember, this triangle had a length of 1/2 and square root 3 over 2. I'm just changing the signs to match whatever quadrant that I'm in. So now I have all of these coordinates on the circle, which really are just a lot of coordinates on a graph. But the coordinates all line up in a circle. Pretend like that was a beautiful circle and not a weird shape. So now that I have all of those coordinates laid out on a circle, I want to actually draw in the radius stretching from the origin to each of those coordinates. So I'm going to start with my first angle that I drew. So my first angle right here was a 30-degree angle. So I'm going to draw in that angle, and I'm going to label it 30 degrees. So my first angle is 30 degrees. But one of the things we do with the unit circle is we don't just measure angles in degrees. We measure them in radians. So a radian is another way of measuring an angle, and it's related to how many times the radius can go around the entire circle, around the circumference of the circle. So the conversion rate is that to go from degrees into radians, you multiply by pi over 180. So 30 times pi over 180. So 3 over 18 is 1 over 6. So we end up with 1 pi over 6. So we say that 30 degrees is pi over 6 radians. So I also am going to label this angle as pi over 6. Okay, and then once I have that one done, I'm going to go back and I'm going to draw in this second angle that I had, which was a 45-degree angle. And if I bring back my protractor, we should be able to see that. Yeah, that's 45-degree angle. So this angle right here from the x-axis to that radius that I drew is 45 degrees. So I'm going to label it 45 degrees. And then again, we can convert 45 times pi over 180 simplifies to pi over 4. 45 goes into 184 times. So 45 is pi over 4 in radians. So I'm going to label this pi over 4. And then moving on to my next section, I can sketch in this angle. And when we measured this angle at first, we measured it to be 60 degrees. So I'm going to label this segment as 60 degrees. The line isn't 60 degrees. It's the angle, again, from the positive x-axis to that point. that would give me a 60-degree angle. And again, we can convert 60 times pi over 180. Ends up giving us pi over 3. 60 goes into 180 3 times. So we end up with pi over 3, which is how we would measure this angle in radians. And then we're going to actually keep going around the circle. So our next angle would be to this point up here. And we didn't actually measure that on the protractor, but I could bring back my protractor and measure it, and we'll notice that it's sitting at 90, which hopefully you can recognize that this angle right here that we're measuring from the positive x-axis to our line is a 90-degree angle. So I'm going to label this as 90 degrees. And if I convert that into radians, 90 times pi over 180 would give me pi over 2. So 90 degrees is pi over 2 in radians. Let me get rid of my math up here. And then I'm just going to keep going all the way around the circle, doing the exact same thing. But now I'm going to start to use some pattern recognition to help me out so that I'm not having to do quite as much math. So I've sketched in this next angle, and I didn't bring out my protractor to measure this one. I created this segment, or this part of this point on the circle, using triangles. I never actually measured this with a protractor. So I could bring out the protractor and measure this angle, and we'll see that it's at 120 degrees. So I'm going to go ahead and label it as 120 degrees. But another way to think about this is we had a 90-degree angle already going up to this point, and then from there, this segment right here, this section, is the same as this first angle that we started with, which was 30 degrees. So 90 plus another 30 lands us at 120. And we can convert 120 into radians by multiplying by pi over 180. And this one would simplify to 2 pi over 3. So in radians, this is 2 pi over 3. And then for my next angle, I'm going to draw that one in. All right, and then this angle, again, if I measured it, I could figure it out, but I have my 90 degrees already. And then this distance right here is the same as this distance, which was 45. So 90 plus 45 is going to give me 135 degrees. And 135 degrees, if we multiply by pi over 180, is going to end up giving us 3 pi over 4 in radians. And then my last angle that I want to look at is this one right here. And so again, instead of measuring this giant angle right here, which I could do with my protractor, I'm going to say that it's 90 plus this distance, which is the same as this distance, so 90 plus 60, which is going to give me 150 degrees. And if I do 150 times pi over 180, I'm going to end up with 5 pi over 6 for my angle in radians. And then I could go over to my next point over here, and this big angle right here, so we are always starting at the positive x-axis, so this big angle that we're measuring now is a perfectly straight line. A perfectly straight line is 180 degrees, and if we do 180 times pi over 180, we end up with 1 pi, so just pi for this angle when measured in radians. So there's the top half of our unit circle done. So from this point, when I go to measure all the rest of the angles, I kind of do a shortcut. I don't actually calculate all the angles. I kind of have a pattern that I follow. So I noticed that my pattern for my first quadrant, I added 30 plus 15 plus 15 plus 30. That's to get all my angles in degrees. 30 plus 15 is 45, plus 15 is 60, plus 30 more gives me 90. If I did that same thing, I can add 30 plus 15 plus 15 plus 30, and that'll give me all of my angles in degrees. So I'm going to follow that pattern into the third quadrant. So I'm going to take my last angle measure that I had, which is 180, and I'm going to add 30 to that because that's what this angle is, 30. So 180 plus 30 would give us 210 degrees. And then I'll come back and do the radians in a minute. And then 30, and then the next part of the pattern was plus 15. So 210 plus 15 is going to give me 225 degrees. And then again, following the pattern, 30 plus 15 plus 15 again. So 225 plus 15 is going to take me to 240 degrees. And then again, following that pattern, 30 plus 15 plus 15 plus 30. So 240 plus 30 gives me 270 degrees. And that makes sense. 90, 180, 270. If we add 3 right angles together, we would end up at 270. And I'm going to keep following that pattern. 30, 15, 15, 30. So I'm going to sketch in my next segment. And I'm going to add 30 to my previous angle. So 270 plus 30 gives me 300 degrees. And then after that, it's 15 that I need to add. So 300 plus 15 would be 315 degrees. And then I add 15 again, which would give me 330 degrees. And then the last part of the pattern is to add 30 one more time, which would give me 360 degrees. Oh, and I could also say I started at 0 degrees. Going all the way around the circle would be 360 degrees. Hopefully it makes sense. We know that there's 360 degrees in a circle, so it makes sense that we ended up at 360. So now I need to go back and add in all of my angles and radians because I kind of skipped that part once I got to the pattern. So I'm going to go back in and add all of my angles in radians. Let me move this so that it matches the rest. This was 300 degrees. So rather than just multiplying by pi over 180, which you can always do to figure out your angle in radians, I'm going to start looking for a pattern. So I'm going to start with pi over 6. So we have pi over 6 for that distance. And then this is another pi over 6. So that would be 2 pi over 6. But if we wrote 2 pi over 6 and simplified that, we would end up at pi over 3. And then if I go that distance again, I would have 3 pi over 6. And if I simplify 3 pi over 6, I get pi over 2, which matches which was over here. Then after 3 pi over 6, it would be 4 pi over 6, which would simplify into 2 pi over 3. And then 5 pi over 6, which is what I have written. So my strategy that I use here is I just start adding 1 to the numerator. If it simplifies, then I don't write it down. If it doesn't simplify, then I know that that's going to match up with my next part of my unit circle, my pi over 6 segment. And I'm calling this my pi over 6 segment because it corresponds with all of my other pi over 6 coordinates. So I know that this is going to have a denominator of 6. It's going to be something pi over 6. Now I just have to figure out what pi over 6. So I ended at 5 pi over 6. After that, I would check 6 pi over 6, which would simplify to 1 pi. And after that, 7 pi over 6 does not simplify. So that angle, I'm going to label it as 7 pi over 6. And then I'm going to do the same thing with 225 degrees. Rather than multiplying by pi over 180, I'm going to look at my pi over 4. So I had pi over 4. 2 pi over 4 would simplify to pi over 2. 3 pi over 4 is in the second quadrant. 4 pi over 4 would simplify to pi. So now I'm at 5 pi over 4. So 225 is 5 pi over 4. My pen's a little too big. 5 pi over 4. All right, and then for 240, that corresponds to all of my pi over 3. So pi over 3, 2 pi over 3 is in the second quadrant. 3 pi over 3 simplifies to just 1 pi. So now I'm at 4 pi over 3. And I can keep going. So then my next section is another pi over 3 because those coordinates match. So 4 pi over 3, then 5 pi over 3. Next I have a pi over 4. And I've got this color-coded, which helps me recognize that. So after 5 pi over 4, 6 pi over 4 would simplify. So that's not going to be on there. So then I get to 7 pi over 4. So that goes here, 7 pi over 4. And then I'm going to end up with another pi over 6. So 7 pi over 6, 8 pi over 6 would simplify, 9 pi over 6 would simplify, 10 pi over 6 would simplify. So that leaves me at 11 pi over 6 for my last one. And then the only one that I'm still missing is 270 degrees, because that corresponds to a pi over 2. So I had no pi over 2, 1 pi over 2, 2 pi over 2 would simplify to pi. So now I'm at 3 pi over 2. And if I kept going, 4 pi over 2 would simplify to 2 pi. So 360 degrees or 2 pi. So that's my entire unit circle. I'm going to actually draw in lines here as well on top of my graph. So now if I take away my XY plane, I have this massive circle that we call the unit circle. But all of that comes from this construction of triangles using these 45, 45, 90 and 30, 60, 90 triangles. So it's not just a random circle with a bunch of random numbers. And then all of these points that I have drawn are really just points on a graph. So that's how we end up with the unit circle that we started with in the beginning. So here's the unit circle that we started with in the beginning with all of that information written down on it, and then the unit circle that we constructed. So there we have it. That is the unit circle. Now, the reason that the unit circle is important, and I'm going to take away my unit circle and put the prettier unit circle up. The reason that we consider the unit circle important is because it allows us to figure out information about trigonometry, specifically sine, cosine, tangent, and then we also have cosecant, secant, and cotangent. So we have the 3 trig functions that you learn in geometry and 3 more trig functions that show up in pre-calculus. And all of these trig functions can be described using the unit circle. So I'm actually going to bring back one of my triangles from earlier. And I need to edit this triangle a little bit. So this triangle that I had earlier corresponded with 30 degrees, or pi over 6, and we said that it had lengths of square root 3 over 2 and 1/2, and that's how we got the coordinates at pi over 6. So I'm going to take this triangle for a second, and I'm going to go back and I'm going to do some geometry with it. So I know that this is 1, this is square root 3 over 2, this is 1/2, and this angle is 30 degrees. And I want to find sine of 30 degrees. So if we go back to geometry for a second, we have the acronym SOHCAHTOA, and we're looking at sine. So sine is opposite over hypotenuse. So we want to find sine of 30 degrees for this triangle. Sine is going to be opposite, which is 1/2, over the hypotenuse, and the hypotenuse of this triangle is 1. And this is why this triangle is so beneficial for trigonometry. We could find sine of 30 using any triangle with a 30-degree angle. But the fact that the hypotenuse here is 1 makes this math really simple, because anything divided by 1 is just itself. So sine of 30 is 1/2. No matter what triangle you're looking at, if it has a 30-degree angle, sine of 30 is always 1/2. So I could draw a much larger triangle, and now I know for a fact that sine of 30 is going to be 1/2. And even if I'm not looking at 30, if instead I'm looking at sine of, I labeled that 30. Yeah, so sine of 30 is the same as sine of pi over 6. So if I wanted to find sine of pi over 6, it's the same as sine of 30, because 30 degrees is equal to pi over 6 in radians. So sine of pi over 6 is 1/2. Well, what's beneficial here is not just knowing this triangle, but knowing 1/2 was the y-coordinate of the point that was on the unit circle. So again, if I bring back my unit circle for a second, this point right here at 30 degrees had a y-coordinate of 1/2. So my rule is that sine of theta is just standing in for an angle, is equal to the y-coordinate of that angle on the unit circle. So if I wanted to find, let's see, if I wanted to do sine of 7 pi over 4, I'm going to go look at 7 pi over 4, and I'm going to look at the y-coordinate, and I know that that's negative square root 2 over 2. Okay, then on the flip side, going back to just my triangle, so we talked about sine. If I wanted to find cosine of 30, SOHCAHTOA, we're in the co part of SOHCAHTOA, cosine is adjacent, which is square root 3 over 2, over the hypotenuse, which is still 1. So cosine is square root of 3 over 2 divided by 1, and anything divided by 1 is itself. So cosine of 30 is square root of 3 over 2. And again, if we go back to our unit circle, square root 3 over 2 is the x-coordinate. So our rule is cosine of theta, where theta is just the angle on the unit circle, is equal to the x-coordinate of that point on the unit circle. So if I want to find cosine of 240 degrees, I'm going to go look for 240 on the unit circle, and I'm going to find the x-coordinate, which is negative 1/2. So cosine of 240 degrees is negative 1/2. And I could use this for other trig functions as well. I just have to know the ratio. So if I want to find tangent, I could say tangent is opposite over adjacent and figure it out that way. But it's beneficial to know that tangent is sine over cosine. That's a ratio that you need to have memorized, that tangent is sine over cosine. So if I want to find tangent of pi over 6, so that first angle that we're looking at, I need to do sine over cosine, or we just said that sine is y and cosine is x. So sine over cosine, y over x, tangent of pi over 6 would be 1/2 over square root 3 over 2. And then I could keep, change, flip, and simplify that, and then rationalize my denominator, and get tangent is square root 3 over 3. And this works for any trig function. So tangent is sine over cosine, so it's y over x. But I could keep going. So tangent is sine over cosine. Cotangent is cosine over sine. So cotangent is x over y. So I could find cotangent. If I needed to know cosecant, cosecant is 1 over sine, so cosecant is 1 over y. Secant is 1 over cosine, so it's 1 over x. So the reason the unit circle is so helpful is because it allows us to figure out a lot of information about all these different trig functions. Now the unit circle is really hard to memorize. I'm going to post a different video with a trick for how to memorize the unit circle. That way you're not having to construct the entire thing using triangles every single time you need to know it. And also so that you're not having to memorize all of these different quadrants all around the entire unit circle. So when you're finished watching this video, if you don't have your unit circle memorized and you need help, go to the next video so you can figure it out. Hope that makes sense. Ask me questions if you need to.